Now it seems okay. So I'd like to start today's lecture. So the title is some sharp null-form type estimate for the Klein-Gordon equation in space-time dimensions by Dr. Shobu Shiraki. Before I start the lecture, I'd like to introduce him. Dr. Shiraki has gained his degree 2 years ago, I suppose. 1 year ago, but under the supervision of Professor Neil Bass in Saitama University. His major is harmonic analysis with applications to PDE. Actually, his concerns PDE, but main tool is fluid analysis, fundamental estimate of fluid analysis, and so on, so on. And let me add that he also studies fractional Schrödinger equation, and compatibility of time limit, and he published some papers. I think that he's a very brilliant mathematician in Japan, so I'm interested in his talk. So now it's the time to start. So please start.
Kind introduction. And I would also like to thank Donald for working on this. It's very cool. So today I'm gonna talk about my recent work with Jason Knanen, who work at Saitama University last year. The key word here would be sharp strictest estimate, null-form, and Klein-Gordon equation. And as an introduction, I'll give you 3 topics: wave, null-form, and Klein-Gordon. Let's start with the wave as the pre-situation for the Klein-Gordon. Let D denote the spatial dimension greater than or equal to 2, and denote T the time variable and X space variable. Then we also define this operator D as this. The multiplier is this modulus of xi, and I use this tilde as the Fourier transform for space-time, and later I will also use hat for the Fourier transform, just a space. I just want to distinguish them to make sure what I'm doing. And the strictest estimate for the wave is stated as following. I guess you know how much useful this is more than I do. But the thing is, you take the LQ norm in time first, and then take LR norm in space to the solution to the wave. Then you control it by some constancy and the homogeneous sublift norm of the initial data. And here the question is very simple. People usually don't care about this constant, no matter what this is. The estimate is kind of enough for the applications, but what exactly is the smallest C? That's the question. And let's denote it by C star, depending on Q, R, and D. And usually, in general, it's very hard to compute the best constant for any inequalities. But in this case, if you're lucky, for some special cases, you can actually calculate it. And here is the some examples of current results. In 2005, Damiano Foschi in Italy found a way to calculate the best constant in 2 dimension with the Q and R 6 and 6, and 3 dimension when Q and R are 4 and 4. This was the sort of the beginning of the series of study. And his tool were Lorentz transform and its invariance and trilinear argument and bilinear argument. And then in 2012, Bez and Rogers generalized his argument into multilinear and found the best constant in 5 dimension. And soon later, Bez and his student at the time, Chris Jevons, found the best constant in 4 dimension by applying this multilinear estimate combined with Funk-Heck formula from the spherical harmonics. Let's move on to a little bit about null-form. Here we define this box, the D'Alembert by the Laplacian in space subtracted by the second derivative in time. And suppose U and V's are the solution to it. There are actually several kinds of null forms, but the one related to here is this Q of UV, defined by the product of the derivative in time subtracted by the inner product of the derivative in space. Then the critical space-time estimate for this is this L2 norm of the null form. Then this can be expressed in the language of the operator D plus and D minus, which is defined by this. Here we have tau information as well as the multiplier. Then in general, to deal with all other null forms, people want to know how behave or when this inequality holds. On the left-hand side, we have 3 parameters, beta 0, beta plus, and beta minus. And then the one we are considering now is the case when beta 0 is 0 and beta plus is 1 and beta minus is 1. And then you control it by the initial data with two variables, alpha 1 and alpha 2. And this crucial estimate can be further simplified by spreading into two inequality called plus plus and plus minus. It's called plus plus because we have a plus wave and plus wave here. And then the second one is called plus minus because we have plus wave. And if we put this complex conjugate here instead of here, then that's minus wave. So we call that plus plus and plus minus. And these two are main object that I'm gonna consider here. And especially this plus minus because it's much more difficult than plus plus. And while we are considering L2 norm here, the general form, the LQLR, has been also studied by very serious authors like Bogan, Lee, Rogers, Tao, Totoro, Vargas, Vega, and Wolf. And here is a very brief history of the null form and the best constant. So in 1993, Klein-M and Amakeden studied null form for wave. And then Ozawa and Tsumi took their idea in the context of Schrödinger and discussed the nonlinear applications. And and they also discussed best constant. And then for the Schrödinger, for instance, Carneiro, Plotchenberger studied it with another null-form in 2009, and Bennett, Bez-Jevons, Paticus in 2017 consider this type of null-form as well. And in 2000, Forsky and Kleineman completely understood the crucial estimate for the null-form. In other words, they revealed the properties of beta 0, beta plus, beta minus, alpha 1, and alpha 2. This is for L2 case. And for LQLR, I believe it's almost done, but there is a still open problem in 2-dimension. So if you're interested, you can do something about it. In 2016, Bez, Jevons, and Ozawa studied this new form of wave and also obtained some best constants. These two are the new form they considered. And very recently, Beltran and Vega applied Ozawa-Tsumi's argument to Klein-Gordon so that they considered this new form. So it's very active field. And in contrast to this Beltran and Vega results, we take the spirit of this Bez-Jevons-Ozawa's argument and extend it from the wave to Klein-Gordon. Right. Then for the Klein-Gordon, let's define this Japanese bracket of xi by the square root of 1 plus xi squared. Then similarly, the strictest estimate states that this, the differences were colored by green. So now we have the Japanese bracket instead of just modulus. And then the same question is asked, what's the best to see? And then we also denote it by a C star, but this time it doesn't only depend on Q, R, and D, but also alpha, because that time for the wave, we had a homogeneity for the inequality. So once you fix the parameters Q, R, and D, then alpha was automatically determined by them. But now we don't have such nice or could be bad property. So you have some choices of alpha as well. And here's the current results for the Klein-Gordon. Kirijan in 2011 extended Forsky's idea and got the best constant in 2-dimension and 3-dimension. And Jevons did similar thing to 5-dimension. And then there is a non-trivial case in 1-dimension for Klein-Gordon, which has been studied by Carneiro, Oliveira A. Silva, and Salsa. So they found the best constant for 1-dimension. And I put blank here because this was our original motivation for this study. Remember, like the four cases missing. The corresponding alpha is, 3/4. But we failed. We couldn't obtain it, and we will come back with the detail later. And then I like to use the notation, the function phi sub s, defined by the square root of s squared plus the modulus of squared, which coincides with the Japanese bracket when s is 1. And in this context, in this specific context, it doesn't really matter which one you consider, the Japanese bracket or this function. So why not use the generalized one? And formally, with this function, if you let s be 0, then you have the modulus. Then that's the wave case. So this is how the wave and the Klein-Gordons are connected. So before I show you our math, it may not be the worst idea to spend a little bit of time on the results by Bez, Jevons, and Ozawa to see what's similar to or different from our result. So this is their main result. For some beta, they got this bilinear estimate. On the right-hand side, you have the null-form. This can be like this, beta. And you have a plus wave and minus wave, and take the L2 norm. Then on the right-hand side, you have this massive constant, the yellow thing, and you have a blue one. This blue part is written as the integral of the f hat squared and g hat squared in each variables, and the modulus of eta 1 and eta 2, and you have this kernel. And the kernel has this kind of nice structure. All right, how does it work? Here I put their theorem. I omit the constant and literally wrote the blue part. And let's consider very special case like beta is 0 and f and g are the same. Then the right-hand side becomes this very standard L4 norm, the solution. By the way, this is how we get the 4,4 as a QR. Then if you can show that this kernel is essentially the modulus of eta 1 and eta 2 raised to the power, then by using the theorem, so this kernel estimate goes to here, which can be combined with this thing, then you can just spread it into two things. But now we assume that f and g are the same, so we get some this Sobolev no-node, the initial data. So the alpha came from this power plus 1 basically. And in general, this is kind of too strong, but they found that if you give up on the initial data, so just considering the radial data, then for beta in the very wide range, because these numbers are negative in most of the case, you have this Strictest estimate. And this C star is, of course, sharp. This is because if you take out this modulus eta 1 and eta 2 out from the kernel, then by the polar coordinate, you see this has only the radial information, and the remaining thing has only angular information. Then now we're assuming f and g's are radial, so you can put the integral on the sphere here. Then it turns out this thing is just constant. So just reorganizing this and this, you get this right-hand side. And this constant goes to the best constant. All right. Here's our main theorem. The green parts are the difference from the wave case. So first we have a box subtracted by this 2s squared thing. So it's kind of a null form, but it's a bit different. And then you have a plus wave and minus wave, and take the L2 norm. And right-hand side, you have this massive constant again, and the blue parts. And this blue part is written as the integral of f hat squared, g hat squared. And now we have phi sub s of e to 1 and e to 2 instead of just modulus. Then the kernel. Now the kernel looks very complicating, and this is the problem. Right. Then, so I put our result, and then as a remark, first, this constant is sharp, and also this is exactly same as what we've seen in wave. In other words, it doesn't depend on S. And this function is this function is extremizes for this inequality, meaning it makes the inequality equal if you employed it as the input. And again, when S is 0, the result recovers the Jevons-Ozowitz theorem because we have no S here. That means the denominator and numerator are the same. And you have the modulus here. Right. Then our task here is to estimate this kernel so gently that we can have the sublib norm, and at the same time, we have the optimal constant. And there are two ways to do so. The first way is using this key estimate, this one. Then you can kill this denominator, and numerator has, consequently numerator has 1/2 smaller power here. Then this goes to here and here, so that we get this. So this is the kind of kernel now. And actually this is still not so nice, but there are some cases that we can go farther. And the nicest case is when the power is 0, which is the beta is 3 minus d over 4. Then now we have nothing here, so you can just reorganize it into this sublib norm. That's the first one. And then the second nicest case is when the power is 1, which is beta is 5 minus d over 4. In this case, we still have this kernel without power. And by symmetry, you can show that this second term is the positive. So you can just drop it. Then you get this second inequality. In kind of a refined form of Strictest estimate. Then this can be further estimated if you ignore this last term because it's obviously positive, then you get this last one. And moreover, if you look at very special case, when D is 3 for the first one, then that kills this null form so that you have the sharp, by the way, these constants are sharp. So we have a sharp Strictest, standard form is Strictest estimate. Then for the second one and third one, if you let D equal to 5, then again, there's no null form, so that you have standard form of Strictest estimate. And this one, without the null form, this inequality has been obtained by Kirijan, and without null form for the second and third, this has been found by Jevons in their papers. All right, and another Corvalli, which is analogous to the Jevons results result. So let's assume f and g is a radial, then you have this Strictest estimate for rather general beta. The remarks are, if you, there is no extremizer for this inequality. And I forgot to mention, but these three don't have extremizers neither, unlike wave. And this assumption, f and g being radial, actually widens the range of beta. I mean, if you consider general f and g, then beta necessary to be greater than 3 minus d over 4. But because of this extra condition, you can go beyond that. And the similar thing happens in wave as well. And this C star is, of course, sharp. And then the last two remarks are kind of important one. This lower bound, 2 minus d over 4, this may not be the critical. I can tell this is rather a strange number, and I definitely had a technical issue. So it could be, you could be go to lower number for beta. And importantly, there is this annoying gap here. That's the last one. And I believe that this inequality double star holds to be sharp with the same constant, but again, by the technical issue, I believe you can't do anything about it once you take the theorem 1. What I mean by that is this. For beta in the gap, you can find f star and g star such that the right-hand side of the theorem is already bigger than what we are targeting to the Sobolev norm of the right-hand side of the Strictest estimate. In other words, the theorem 1 is too much detour for this thing in this very specific beta, for this very specific beta. So you need rather direct way to attack or to get this right-hand side. And this is very responsible for this this case, our original motivation. So if you want to calculate this, then you kind of need to consider beta is, when the beta is the 4 minus d over 4, then you further let d is 4 so that you kill the null form and you get this, right? But unfortunately, this beta is exactly in the middle of the gap. So this whole argument just can't work for this. So you need a new thing to consider this problem. So it's still open. All right, that was a wave regime. And there is the other framework to estimate the kernel. Here I just wrote our theorem again. So I want to further calculate this kernel. And here we use this key estimate to kill the denominator. So I replace this by s squared to make the whole thing slightly bigger. And we get this constant and the numerator, and it goes to here and here. And then you get these. So this is the estimate we get now, and that's the kernel. Again, the nicest case is when the power is 0, which is this one. And when this power is 1, that's the second nicest case. That's the second one. And if you let d equal to 2, then there is no null-form, and this is what Kirajan obtained in the same paper. And for the second one, if you let d equal to 4, then you get this inequality, kind of a refined form of a Strictest estimate. And this inequality is actually new. I just considering S1 case though. All right, and some remarks on Corvallis. So to show the sharpness, you can consider this function as input with the parameter a. Then for the wave regime, you send a to 0. Then for the non-wave regime, you send a to infinity. But you might wonder why I was missing 2 extra results for non-wave regime, which is the one we simply just drop the last term, and the one we consider only the radial initial data, because I don't know if it holds to be sharp. That's because of if you plug this function into the Strictest estimate, then after the change of variable, you can show that a gets down here. Then you take the limit. So for the non-wave regime, it's okay. It goes to 0 and it's just gone. So it's harmless to ignore the second term, right? Then we still keep this constant as a sharp constant. But for non-wave regime, you have a here and take the limit to the infinity. And that's problem, and I'm not sure if you can do it though, because this second term has kind of information to contribute to the best constant. So that is how I missed the these 2 Corvalli in the non-wave regime. There is also analogous result for a plus case. So you have a plus wave and plus wave this time, and everything is same, like the beta, the blue part and the kernel, except this beta and this constant. the beta is actually, the range of beta is actually widened. So plus has nicer properties. And the best constants are these two. The differences are this green part. Excuse me. Sorry. And again, the plus case is much easier than plus minus case. And I just skipped the analogous Corvallis for plus also holds. Right. We have a, okay, 9 minutes. So let's do the
speak more if you like.
That would be okay, thank you. I just worried about to finish earlier. Okay, so let's look at the proof of the plus case for the theorem, because it's simpler. So for this, let's denote U and V by, the solution by U and V. Then by Planche-Leloup theorem, you have, and the convolution, you get the left-hand side of the theorem here. Then I omit the constant, but it's just Planche-Leloup and convolution. So you have you know the constant, like 2 pi raised to something. And then you can also compute this U tilde as this way, is using the Dirac-Delta function and the initial data. Then this pink part now becomes this. Then using the property of the Dirac function for tau 1 from this guy, I mean, this thing goes to here and here, right? That means tau 1 and eta 1 for the first one. That means that this delta tells us that we can put this eta, the Japanese bracket of eta, here and here. That's this thing. And then you have this. Then we want to use the Cauchy-Schwarz, so just put the Japanese bracket of eta 1 and eta 2 and its reciprocal, maybe raised to the one half. Then use the Cauchy-Schwarz to divide these things into these two. And this brute thing, can be expressed as mu star, the convolution of mu star tau xi, where mu is defined by this. Then it's already known that this mu is a Lorentz invariant, so you can use the Lorentz transform in easy way. Then this thing can be simplified as this. So this is where you use the Lorentz transform. Then now the story is very simple. You can just let eta 1 and eta 2 are equal, kind of, so that this thing goes to squared and you have a 2. Then by using polar coordinate, you can just directly calculate it. And it turns out this brute thing is this thing. Then now we have this guy from the null form. So you just add in them here. That's the kernel. And this kernel and this thing together become the right hand side. That's the very brief proof of the theorem for plus case. And let me finish with this proof of the Corvalli to see how we get this gap. And for this, let me only consider the beta larger than or equal to 3 minus d over 4, this number. And for the smaller numbers, it takes a few more steps. The basic idea, but so let me just do it the simpler one. And also consider S1 for simplicity. In this case, we use, this is because in the wave region, so we use the key estimate, the first kind of key estimate to kill the denominator. So that's this inequality. And the power gets 1/2 smaller. Then because now the power is positive by the assumption, you can ignore this 1. It's okay. Then take this Japanese bracket of eta1 and eta2 out. Then using the polar coordinate, from here you get this. Now the problem is in the wave case, it was easy because this red thing only depends on θ1 and θ2, but now it has a R, the radio information. But we have this lemma. The red for the beta outside a gap, this red thing is smaller than this guy, which doesn't depend on the radio information. And this is exactly what we saw in the wave. And you can calculate it like this. And by using the beta function, you see that's just a constant. So again, you have this remaining thing and just reorganize it into a Sobolev norm. That's how we get the right-hand side of the Strictest estimate. To prove this lemma, I like to consider this as like a parameter kappa living in between 0 and 1. Then you can show that this whole thing is monotonic increasing with respect to this kappa. So just put the 1 is the biggest. That's this right-hand side. And the beta and the gap, it's reversed. So when the whole thing is monotonic decreasing, so this thing is less than or equal to the one you put 0. That's not what we wanted, and this is where we failed to deal with this beta. I put the solution to show the monotonicity, but it's just easy, and you can see later. Thank you very much for listening. That's all.
Okay. Take any questions or comments? Thank you for a nice talk. Is there any questions or comments? So I'd like to ask you a question. So could you please open page 35, the last page, last two page, 30, page 35.
Last page.
Yes.
Ah.
Oh.
Okay. Oh, you want me to explain the last page or?
Yes, actually, so I'm interested because so
Oh,
also
okay, okay. All right.
web
No,
function
no.
is increasing.
All
Of
right.
course, you have time, but I definitely would like to know.
All right. Yeah, right. To show this, just you differentiate it. I put kappa. That was this thing, and using the uh,
Okay.
the the change of variable.
Yeah.
This this right hand side is actually this thing with some constant.
Yes.
Then what we want to show is the monotonicity.
Yes.
So this A is the power, this thing. So D minus 3 over 2 minus 2 beta.
Okay.
And if you differentiate it, so the thing is, it's not true that if you ignore the integral, then you can't say this thing is uniformly
This is
like
why. This is why.
yeah.
So
So
this
you
is why
need
there's
an integral. Then just differentiate it. Then you have a here. Then you split it into you split the integral into two parts. Then change your variable. You like lambda to the minus lambda for this second one. That's this guy. And then by the Jacobian, so you have so yeah, right. By the Jacobian, it becomes plus. No, sorry, Jacobian doesn't matter, but this lambda make this sign plus, and this squared is nothing. The lambda, you have a minus. So anyway, this second thing becomes this guy. So you can just compare these two. Otherwise, they're same. And then the power matters. And yeah, if A is in between 0 and 1, that's the gap. You have the opposite, like negative. So you have monotonic decreasing. Right. That's it. It's very simple.
Okay. Okay. I see. It's quite fundamental. But you have to integrate. So to obtain such inequality, you have to integrate over sphere or something like this. You have to. It's not,
yeah, because here's only after the polar coordinate, we only have the angular information here, so you get
that's why.
the integral of sphere anyway.
I see.
And because by the known result, we knew the best constant would be same as the wave, so we try to reduce the whole case into a wave, the result in the wave.
I see. Okay. Is there any questions or comments? If there are no questions, I'd like to close this talk, but I'd like to invite you to coffee break. The coffee break starts at 2 o'clock Japanese time, after 10 minutes. And please note that Zoom ID is different from this ID, so be careful. So for me, this is for today. Thank you for the nice talk once again.
Thank you.
Thank you, everybody. Thanks, Shobu. Thanks, Yoshihiro. And hopefully see you all in the coffee break. Bye.
Bye.
See you then.